Okay, so we'll do the support vector machine so I can just get it into the right pointer. Okay, so I just want to start again with the high dimensional view of a data set. Remember, if you have a table where you have sort of points going down and features going to the other side, you can think of these as points being in high dimensional space. And remember, we talked about this earlier. You can think about kind of trying to find a dividing line between these points, the ones that are labeled, okay? Now, let's talk a little bit about how you might do that in a principal fashion. The one method for doing it, which is very intuitive, is you take your labeled points, say your red label points and your green label points, and you would find their centroid, and then you would connect them with a line, and then you would find a plane that is perpendicular to that line. And that's a very close to one of the sort of first methods that people did for this, and this is called the Fisher's discriminant analysis. It's a very simple method, classical method developed a very long time ago, and this shows the mathematics for that. The key idea here is that you're kind of finding the centers of your two clusters, and you're finding this plane that separates them from finding the line that connects them. And the Fisher method is the discriminant method is very similar to this support vector machine method, or you can think of the support vector machine method to some degree as generalizing that. And so we'll come to that in a second now. So this is a very popular method. It's used in all sorts of areas. Obviously, in addition to bioinformatics, we use it. It's used in text classification, image classification, whatever. It's very common, I think, in bioinformatics in use in, say, gene expression analysis to kind of make classifiers and so forth. And also it's used in various genome annotation tasks. So I'm going to show you a gene expression example here, and this is from this Nature Biotech paper from Bill Noble. So here what we have is we're trying to classify tumor into two different types of leukemia, ALL and AML, okay? And what we can do is we can look at, obviously, the gene expression of all these genes, and we can try to see if we can classify it based on that. And so of course, we have some labeled examples, and here's an unlabeled example. And now, of course, we can't look at the 20,000 dimensional space of all the different genes, but let's just look at two different genes here. They're shown here, and we can sort of see, well, for these two genes, they sort of seem to have different levels for the green and the red points. And so here we might be able to easily make a dividing line between these two things. Now, if we had three genes, so now we have the two original genes and we have a third gene, we could make a plane. And like I said, this, of course, in higher and higher dimensions, this will be a hyperplane, in many, many dimensions. But this is the basic idea. Now, the question, of course, is, is there a best sort of plane or line to draw? Now, the Fisher method provides a particular recipe for constructing that plane. The support vector machine has a slightly different way of going about this, but it's a way that I think generalizes to more developed boundaries in a better way. So what you want to do here is you want to find what's called the maximum margin hyperplane. And this is in this two-dimensional example, it would be the line, or in 3 dimensions, a plane, or in 4 dimensions, a hyperplane, that is maximally far away from all the classified data instances. So you can see this plane, we kind of, the points that are closest to each other are these two ones, and maybe this one, and we kind of position the plane to maximize the distance. And mathematically, the way we do this is we think of each of these points as we have a, XY value for this. This is a vector of X is the vector of expression profiles, and Y is a label that labels the thing as say ALL or AML and so forth. It's a class label. Now, if the hyperplane between these two we can represent mathematically in this particular form, where you can imagine as W is this kind of a normal vector to the plane. And then, I won't go through the details, but the key idea is from looking at W, you can kind of figure out the sort of width of this margin here. And then once you find out the width of the margin, you can maximize the width. I'm not going to go into the details of how this is done, but I just want to give you a sense of how people might set this up mathematically. So the idea is you can derive an expression for this, the normal vectors to the plane that's related to the nearby points and maximizing that margin, okay? And the idea is that the solution for this W vector is a kind of linear combination of your initial data points. Now, you might say, what if there's no way of separating your data points by a plane? There's just no way. So there's different approaches. That one thing that we're not going to cover is there's this idea with the support vector machine of having kind of a soft margin. They have these things called slack parameters, which we're not going to talk about in this class today. But there's another idea they have, and that is that maybe we can generalize from a plane to make a more complicated shape. So we can get a little bit of intuition for that if we think about not a plane, but we think of a one-dimensional plane or a one-dimensional line, sort of like a dot. So if we have two groups of things, say here's the AML and this is the ALL, and they're perfectly separable on this line, a dot would be a plane that would separate them, okay? Now, imagine, though, we had a situation that looked like this, where we have one group of things on either side, we have the other group. Now, you can see there's just no way of making a dot or a 1D hyperplane here that will separate these things. So what do we do? Well, we can imagine that we could sort of take our original data points, which remember now are in one dimension here, and we can somehow transform them into a higher dimension. So we're just going to move them into a higher space where we're going to place each point by its original x value, but also by its value squared. Okay, and so then we get this parabolic shape here. And now, lo and behold, in this kind of strange setup, we can actually make a plane that will kind of cut off the bottom of the parabola and separate our points. So this is kind of the idea of support vector machine. We kind of move our data into a higher dimension, okay, with this function that we're going to make up. And in this higher dimension, we can find a separable plane. It's kind of the opposite of the cursive dimensionality. It's kind of like the good thing about going into a higher dimension. And there's a trick. It's just a mathematical trick in the support vector machine that lets you define this function that moves us into a higher dimension more easily, and this is called the kernel trick. So you might be thinking to yourself, well, geez, well, how do I know to make this function that goes, takes our point, x and moves it to x squared? What if it moved it to x cubed, or, x squared plus 5? I mean, there's a tremendous number of ways of doing this, and it's actually very hard to construct this higher dimensional, I guess, not projection, but this higher dimensional, I guess, embedding of your data. But the support vector machine kind of has a trick that lets you get around this. And in this particular trick, basically what you need to do is you only need to think about the distance of points in your high dimensional space, and that's called the kernel, okay? Or how similar they are. And if you can construct that distance, you can effectively mimic this function f without actually having to construct it. Now, I'm not going to describe the math behind this, what's called kernel trick. The important idea is that they have some way of taking the vectors and constructing this kind of dual problem with the vectors. And the key thing in this derivation is there's there's a kind of product between each two data points, a sort of inner product, and that product can be generalized to think of just a kernel between them, and this kernel is some arbitrary thing. And then there's also this multiplier on each point, this alpha, which turns into this kind of Lagrangian multiplier thing, which I'll explain to you is kind of important. So the idea is that in this generalization of it, only some of the data points count to define the boundary in the high dimensional space. And those points have that alpha thing to have a particular finite value, and the other points have an alpha of 0. And so the points that define the hyperplane, these are the things that are called the support vectors. These are the points that are close to the dividing plane, and they actually sort of determine the dividing plane. And this actually provides a lot of intuition. I mean, even though it's a little complicated, the mathematics, these actually provide a lot of intuition, because these points with the sort of non-zero alpha, they provide kind of intuition about the cases that are hardest to classify by the support vector machine. So that's actually a nice feature about this approach. In addition to classifying things, it also highlights the kind of edge cases and so forth. And then there's also the kernel aspect. And the nice thing about the kernel is that you're going to replace the distance in this high dimensional space by this kernel. And we can use sort of any type of kernel, but we can use a whole variety of different kernels between two data points. And one of the things we can do is we can use, for instance, here's a polynomial kernel between things, where we look at the product between two vectors raised to a particular power. People also create Gaussian kernels. And the nice thing also about these kernels is that you can potentially use them for data integration, data fusion. So you can have a number of, say you have features that are both string features and sort of positional features. You can create like a Gaussian kernel for one, and you can just look at their like edit distance or their string distance for the other, and just add them together. And that becomes a kernel. Now, it's very hard to understand what your F, what your function would be in this high dimensional space, but it's not important. You can just put it together by constructing the kernel. So in practice, support vector machines are very powerful methods because they provide a way of fusing very different data types together. You just kind of compute the similarity between each sort of type of data, and then you add it together, and then you have a kernel. So this is a way of doing a kind of classification with image data, nucleotide data, expression data, very different types of data can kind of be used together with this kernel. And I think this is one of the most powerful aspects of this approach. Now, of course, the same issue of overfitting comes about with using support vector machines as any other type of machine learning approach. Now, when you take the decision boundary that you create in the high dimensional space, and then you project it back into the low dimensional space, what you'll essentially get is a curve. So, what was a straight line in your high dimensional space, when you come back to your low dimensional space, it will be some complicated curve. And as that F function or the kernel becomes more complicated, you will be making an increasingly more complicated decision boundary. And so this becomes the decision boundary up until which you're essentially you're memorizing the position of the initial data points. And when you do that, of course, you're overfitting. And that's why it's very important, particularly with these complicated kernels, to do this in a kind of cross-validated framework. Now, I just wanted to say a little bit about the decision boundary and how to think about it in relation to support vector machines, decision trees, and also semi-supervised approaches. So this picture just kind of shows, just in a very high level thing, here's our decision trees. And the key thing with the decision trees, remember, is we're doing an axis parallel splits. So the splits are always on, always sort of parallel to an axis, but then remember we're splitting again. So if we continue to split, we make this kind of jaggy boundary through our space, okay? And support vector machines have a very different concept. What they're doing here is they're finding either a curved or a straight cut through the thing where it's really determined by these close by points. A very different way of thinking about the decision boundary. And then I should just point out there are other methods, for instance, which we're not going to talk about, like k-nearest neighbor method and so forth, that will then can construct a decision boundary in even a different way, and they'll also get a very jagged boundary, but it maybe won't have the same jagged characteristics of the as this, say, support vector machine or the decision trees. And then another aspect of the decision boundary also is we're going to be talking in a second about unsupervised methods. And unsupervised methods essentially look at unlabeled data and try to kind of cluster it or think about it. And there are some methods that try to change the decision boundary in relation to the clusters of the data. So they're kind of, you might think of as semi-supervised methods. They use some aspect of unsupervised stuff and some aspects of the supervised things. And so here you might imagine a situation where you're doing a completely supervised approach. You'll take these data points here that are sort of distributed somewhat differently in space, and you'll construct a decision boundary. But the decision boundary maybe will be very skewed by the fact that the data, even though the positive and negative instances create a boundary, the data has a particular shape in a very high dimensional space, and the boundary might get very skewed. And so if you clustered the things, you might, in just an unsupervised way, you might sort of see this differential distribution of the data, and then a semi-supervised approach might take these two things into account and try to shift the decision boundary in relation to this. This is just a very hand-wavy, high-level thing, but I just wanted to put that out to you.